Buenos días a todas y todos los distinguidos participantes y panelistas. Es un honor darles la bienvenida al cuarto día de las Jornadas Científicas Inria Chile 2023. Este evento ha sido organizado por Inria Chile en colaboración con la Universidad de Concepción, la Pontificia Universidad Católica de Chile, la Universidad de Chile y la Universidad Técnica Federico Santa María, con el apoyo de la Agencia Nacional de Investigación y Desarrollo, ANID. Estos 4 días han sido una oportunidad única para compartir conocimientos, explorar colaboraciones y destacar avances significativos en el ámbito de las ciencias digitales. Les informamos que el idioma oficial del evento será el inglés, por lo que continuaremos en dicho idioma. Good morning to all distinguished participants and panelists. It's a honor to welcome you to the 4th day of the Scientific Sessions Inria Chile 2023. This event has been organized by Inria in collaboration with Universidad de Concepción, Universidad de Chile, Pontificia Universidad Católica de Chile, Universidad Federico Santa María, with the support of the Agencia Nacional de Investigación y Desarrollo, ANID. We have gathered in the past few days at the Catholic University, Universidad de Chile, and yesterday at Federico Santa María Technical University in Valparaíso, and today we begin our 4th and final session at the Universidad de Concepción. These 4 days provide a unique opportunity to share knowledge, explore collaborations, and highlight significant advances in the field of digital sciences. Now it's my honor to introduce the welcome words of Andrea Rodríguez, Vice President for Research and Development at Universidad de Concepción.
Good morning, everybody. Welcome to the University of Concepción. I would like to greet all of you, authorities from Inria, to strengthen also the importance for the University of Concepción to have the opportunity to create a space to increase the collaboration between France and Chile. University of Concepción is a university that covers different areas, but science and technology in digital science and technology is one of the important ones, because we think that is something that is basic and give the opportunity to develop other areas where we are working. So especially we will like to see how this scientific day organized by Inria and us can help us to strengthen collaboration in areas where mathematics, modeling, science in different areas as oceanography, where we have been working together with you in the past days with the Ocean Hackathon that was held here, and it was very successful in our opinion. And also because we are in the University of Concepción trying to pursue further development with a new doctorate degree in artificial intelligence. A doctoral degree that is in collaboration with the other 3 universities. And we are very happy to know that we have many applicants for this year, so we hopefully have talent that is coming and we can strengthen this area in our university. I cannot say anything more besides that we have in the past some collaboration with Inria, with France in particular, and we think that we need to increase this collaboration. It's good, but we need more, because international collaboration basically, I will say that strengthen the importance and impact of our scientific production. So we are really happy to have you here. I hope these days will be very successful, and we will be looking after the days what will happen, so that we not only have good talk, but we have something then. So thank you very much.
Thank you, Ms. Andrea Rodriguez, for sharing your insight and vision with us today. Now I leave you with Sofia Valenzuela, Regional Secretary of Science, Technology, Knowledge, and Innovation. We warmly invite her to share a few words with us.
Good morning, everybody, and thank you for the invitation to be part of this Journées Scientifiques, which are very interesting for us as a Ministry of Science. I know you have been in Valparaíso, Santiago, and it's an honor for us that you come here to Concepción, which is the second city after Valparaíso that has more research and development, and also our ministry has more projects within this region. We have had, for our ministry and our president, Gabriel Boric, the internationalization of our research in Chile is very important. We know that we have very good talent. It's a challenge, though, to keep that talent in Concepción. Most of the time, they tend to go to Santiago or abroad. And for us, we want to have more people staying here in Concepción, not only from Concepción, but also from other countries. Why not from France? So also the invitation is to have some of you researchers come and make a stay here at Concepción. We have a great ocean. We have a lot of research in oceans. We have also forestry as one of the areas, agriculture, a little bit less now that Ñuble, which was part of our region, now is an independent region. But I think there are many, many possibilities of collaboration between Concepción and different parts of France, and the invitation is here. Us, as Ministry of Science, we will do everything possible to increase the collaboration through projects or others, and we hope to have more people here in Concepción, to stay here at Concepción, do research from Concepción that can have an impact not only in our region, but in our country and abroad. So thank you very much.
Ladies and gentlemen, before we proceed, let's express our sincere gratitude to Sofia Valenzuela for her words. Now I will invite to the stage to Cécile Bigorou, Director of International Relations at Inria.
Okay. So thank you very much for giving me this opportunity to say a few words this morning. So I'm very happy to be here today. It's my first time in Concepción, and I hope not the last one. But I heard about your university before coming, and especially, as you already mentioned, Andrea, the fact that there are collaborations already ongoing between Inria and your university, and we really want to have more, and especially through all the work that Inria Chile has been doing for more than 10 years now, we really think that according to the topics that we are both willing to develop, and especially AI, because you mentioned this new PhD program in AI that was mentioned to us a few days back when we had a meeting at the Ministry of Science back in Santiago. So it's really important program for us as well. And I think this is something that we are going to develop within the frame of Inria Chile as well. So just maybe a few words about Inria, because there might be some people not that familiar with Inria. So we are the French National Center dedicated to digital sciences and technologies in France. We have 9 research centers all over France. And not only are we, of course, addressing all the challenges in our fields of expertise in research and having a very high level of excellence in research, but we are also work very strongly in transfer and innovation from the very beginning of our creation. We have been working on these 2 pillars from the very start, and more recently, and this is something that may be of interest for the researcher in the room today, we are also working closer and closer with our university partners. And at Inria, actually, we don't work in department or laboratories, we work in project teams. We currently have a bit more than 220 project teams, and these project teams are made of researchers from Inria, but also researchers from universities or other French institutes. So you may be already working with people that are strongly connected with Inria, but you just didn't have the opportunity to discuss it. And the fact that we are really building this collaboration stronger and stronger with universities will also improve the other aspect that was mentioned by Sophia, the exchange of researchers and maybe also of students, because through the different training programs such as the PhD you mentioned and also master's program, it will be also an opportunity to have more exchange of students. And the last pillar I wanted to mention is the support to public policy. And this is something that we are really strongly involved in Inria Chile, because Inria Chile is, of course, covering research, transfer and technology, but also support to public policy. And we are currently having our collaboration evolving between Inria and Chile, and we are working together to have something that will be really customized in order to support the policies from France and Chile in Chile through Inria Chile. So I'm very happy once again to be here today. And before I leave the floor, I really want to thank the organizing committee. And I really want to thank all the people from Inria Chile. So Nayat, Luis, where is she? Julia, Paloma, and Enrique, Roberto, Jorge, that saved my life this morning. So definitely thank you very much, because you've been organizing a great event. We have very positive feedback from all the participants. And it's the first time we do it that way. And it's the first time I'm controlling Nayat, she will tell me that we are also doing it here in Chile. So I think it is really the first seeds, so to speak, of a very fruitful collaboration. Muchas gracias.
Thank you, Cecile, for those warm words. Means a lot to us. Now I will hand over the floor to Najat Sanchez P., Director of Inria Chile.
Hello everyone. Morning, bonjour à tous et toutes. Buenos días a todos. Welcome to this fourth day of the Inria Chile Scientific Days. Ms. Sofia Valenzuela, Science, Technology, Knowledge and Innovation Regional Ministerial Secretary. Andrea Rodriguez, Vice President for Research and Development, Universidad de Concepción. Cecile Goro, Director of International Relations at Inria, researchers, academics present, directors of Centers of Excellence, colleagues, friends. I'm delighted to welcome you to the final day of this Inria Chile Scientific Days 2023, hosted today by the Universidad de Concepción. It is a privilege, really, indeed, for us being here in the heart of the Biobío region, a land known for its natural beauty, rich history, but also for its innovative spirit and also scientific inquiry. Our scientific caravan with Inria researchers that travel from France, especially for this occasion, stopped today here in Biobío region, after 1 day in Valparaíso and after 2 days in Santiago, in the metropolitan region. Today's gathering here really marks a significant milestone in our shared journey of scientific advancements and innovations. The Biobío region holds a special place for Inria Chile, as it represents a hub of technological excellence and a cornerstone of our long-standing collaboration since establishment of Inria Chile in 2012. And especially the University of Concepción, with its long-standing tradition of research and innovation, has been a central pillar of our collaborative efforts. Over the past 3 days, we have embarked on a remarkable journey, delivering to the frontiers of the digital sciences and forged new connections across different disciplines: health, energy, climate change, astronomy, agriculture, resilience, marine biology, and our discussions so far have sparked inspiration and ignited a shared passion for scientific advancement, turning our attention to 2 key areas: the impact of digital sciences on society and the future of scientific collaboration. Today's program promised to be equally stimulating, with a focus on intersection of AI and modeling, as well as further advancements on computing with many other sectors. As we engage in these discussions, let us remember the power role that we have as researchers and scientists in shaping our future. Our collective knowledge, creativity, and dedication holds the potential to address the challenges of our times and create a world that is more sustainable, equitable, and prosperous for all, and for everything that we need for collaboration. I encourage each of you to participate actively in the sessions, share your perspectives, and draw inspiration from the participants. The connections that The ideas exchanged during these final moments will resonate far beyond the walls of this university, paving the way for a brighter future for science society between France and Chile in digital sciences. I would like to extend my gratitude to the scientific committee members of the Journées Scientifiques Inria Chile, and especially the members of Concepcion University for their dedication, expertise, and unwavering support for shaping the exceptional program we have before us today. My sincere gratitude also to the organizing committee team of the Inria Chile that has done a great job, and also the local team of the university that hosts us today for the hard work in the organization and also the tough logistic. I hope you can make the most of the Inria French-Chilean network of researchers that we just platform that we will on top of the 11 years of collaborations and we just formally launched last year to host more collaborations between India researchers and France and Chile in digital sciences. Thank you for your commitment to scientific progress and collaboration. Let us make these final days of the India Chile Scientific Days 2023 a last testament to the transformative power of digital sciences and the spirit of international partnership. Thank you.
Our sincere appreciation to Nayat Saint-Esprit for your continuous leadership and dedication to fostering a vibrant research community. Inria Chile contributions under your guidance have been remarkable. Thank you very much. Now let's proceed to the scientific session 4.1, Understanding Natural Processes 2, shared by Camila Fernández, Copas Costal, Universidad Concepción, CNRS.
Thank you, Nayat. Thank you, Andrea, and everybody. It's a pleasure to be here. I'm honored to have been asked to chair this session on natural processes, understanding natural processes too. I just have to say that it's remarkable to host Journées Scientifiques in 3 different cities in 4 different days. It's kind of a marathon of digital science. And it's thrilling. I've been following the development of the other Journées, and it's been an enrichment, and we hope that this last day will be as enriched as the other ones. So let's kick in. In the subject, we will have a keynote speaker now, is Nicolas Brodu, a member of Inria Center in Bordeaux in France. From the project team Geostat in Inria. Nicolas has a double training in physics and computer science. He's a chargé de recherche at Inria since 2016, and he also has an HDR since 2021. Currently, he's the leader of Geostat project team in Inria, and he's a member of the Bureau of French Association of Artificial Intelligence since 2009 and until 2011. So he has extensive experience in the domain of digital science applied to the environment. The title of the presentation is Inferring the Effective State Variables and Dynamics from Data. Thank you, Nicolas. The floor is all yours.
Hi, everybody. So today the topic of my talk will be to model complex systems, which you can find in pretty much every disciplines. So what do we mean by complex systems? It's systems in which you have elements interacting at different levels. So here I say it's a forest, so you have elements at each microscopic, like the trees and their roots and root-to-root interaction and so on. So if you want to model this using mechanistic approach, then you will have to aggregate a lot of these sub-models. And usually the global model you obtain by aggregating all of these things becomes bloated, and you cannot fit it to data. So it's the usual approach, gives the best interpretability, but you have an issue if you want to model something at the scale, say, of a forest. On the other hand, machine learning does the opposite. It starts with observations which are made usually at the global scale, like a flux tower would monitor the CO2 flux at the scale of a field, and doesn't go down to the mechanism of what produced that data in the first place. So then that's fine because you get a model at the scale of the measured data, but you cannot go back to mechanisms, so it gives you less interpretability. So that's what I said in a more abstract setting. So mechanistic models are difficult to aggregate and machine learning difficult to interpret, usually, not making specific assumptions here. One approach which has been used for a long time in statistical physics, when you have elements in interaction, is to aggregate them by configurations of the same energy, and then you get state variables. So if you have molecules in a gas, then you can get state variables such as temperature and pressure. And once you do this, you can relate these state variables together and get like a global description at the scale of like the container, say, for a container containing molecules of a gas, such as the perfect gas law. The problem is when you have a forest, then you cannot aggregate all of these sub-elements here because they are not like molecules. It's too complicated to aggregate them with such a method. So what you do here, what we propose to do is gather the past histories, the state of the system, which has the same predictive information on the future, and still get state variables, but at the scale of what you measure. So by analogy with statistical physics, we are designing new models and gets the effective state variables at the scale of the system. And similar to having laws here, you would get predictive laws, a bit different. So now let's put this concretely in practice so you see what I mean. So case study here is the monthly sunspots. So you have here a time series from the 1750 to the nowadays, consisting of the number of sunspots every month. It's one of the longest measurements in history, like continuous measurement, observations. And if you apply the method I just told you, and supposedly it should be like big here on the screen, but it's not for some reason. When I mention state variable here, what you get back is here two state variables, x and y, which gives you that 11-year cycle. And that 11-year cycle, if you look at the data, is the most prominent feature at a global scale. But you see that you also have these variations here, such as these large variations on the scale of 80 to 100 years. And these variations are captured by the algorithm as the third dimension. So you get effective state variables in which you can describe a trajectory that that will make you able to predict what goes next. So it allows you to model what goes on. So it resembles an attractor, and then you can make predictions. You can either stay on the attractor, what I did here in red, so you force the trajectories to stay on the attractor, or you can use linear operator, such as a Koopman operator for those who do dynamical systems. And that will converge slowly and progressively to the average here of the trajectories. In data space now, not in effective variable space, the predictions look pretty much like the same as you had before. So it's just one possible trajectory against a stochastic system. So you would get an ensemble of trajectories as predictions. But one of them here, you see that the statistics look pretty much like before. And if you take the linear operator, or the Koopman one if you want, then you would converge to the average of the system. And the average is the best predictor in the long term for the values you would get. So that's another way to model systems. And it's based on the notion of causal states, which was invented by or discovered by Jim Crutchfield at the end of the 80s. So I will take a few minutes to discuss that now. The idea is to say I have observations, so many observations, heterogeneous data sources here. And I'm going to gather together the possible futures that has, no, the past that has the same distribution of futures. So imagine you have past 1 and past 2 here, and each of them, like observe past in blue, yield the same outcome. So whether you're in past 1 or past 2, you will observe the same thing later on in statistics. So same distribution of future given the past. The idea is to make equivalence classes here of the same information on the future. So that's what I mentioned in introduction. Gather system states, so system histories, which has the same impact on the future. And these equivalence classes now have nice properties. The first property is that since you are gathering future distributions, no matter what new observation you will make on the system, then it won't allow you to discriminate where you came from. So for all modeling purposes, then these equivalence classes are all you need to be able to predict the future distribution. There is no point in keeping these past histories and where you came from for modeling in a predictive setup. And the second property is that they do not depend on the frame of reference. And that's a huge thing in physics, which means that you can change your referential, change the way you measure your variable, and that would change maybe the shape of the distribution here, but that would not change the equivalence class. Meaning that what you try to infer here as a physical meaning, it's an intrinsic property of what you observe and not your observation mechanism. So now back to physics. You can view the ODEs as a special case of that setup. Just because in ODEs, as you well know, you have each point in the phase plane here. So that's the state space is the angle and angular momentum, sorry. So for that dissipative pendulum, say, it goes back and forth. And in the state space here, each point has its own future. As you well know, in ODEs, trajectories do not cross. So in that case, each point here has a unique future. So the distribution is a delta distribution on that unique future, meaning that for that specific case of ODEs, each point in the phase plane is its own causal state because it has a unique future and it's unique to other points in the plane. So if you want to apply the algorithm, which I will show you later on, to this, it means that what you get as effective state variables are like different parametrization of the same state space. And if you encode the causal states in a set of coordinates, then you get back these E1 and E2 effective state variables, in which you get an effective law of motion, which corresponds to the law of motion of the pendulum, in a different frame of reference, because the algorithm has no way to go back to your original frame of reference. It's independent of the frame of reference, obviously. So it gets another and equivalent description of the system. But again, these are stochastic descriptions. So if you add stochastic noise on your system now, say this adding a stochastic term, the well-known chaotic attractor here, well, same as for the pendulum case, you get back an equivalent description in a slightly different frame of reference, but still you get back an equivalent system. The trick is now if you add some additive noise to the system. So I'm adding to each and every of these points here I'm adding some noise. That does not change the equivalence classes, which means that when you try to recover the causal states, you actually denoise that chaotic attractor pretty well. So that's quite fun. That's already quite good. But now the intrinsic noise, the stochastic noise, which is itself in the equations. So in addition to the ODE here, I've added like this dW, for those who don't know, is just a stochastic term that adds to each incremental in time, it adds a stochastic component, so you can go different direction at each step. So if you do this, then the stochastic noise is preserved by the causal state transformation. Oops, sorry. See, you can look at the small details here. Anyway, now, obviously, I'm missing an important step here. I'm considering distributions of sequences of future given past, and I'm considering them as points. So when you had that every point in the state space correspond to a causal state, then it's a delta distribution, makes these things obvious. But, oops, don't like this system. In general, what you do is you need to embed a function, like that distribution is itself a function, into a functional space. And once you do this, the distributions become points in that infinite dimension space. And one way to do it is with reproducing kernel Hilbert spaces. That's only one possible way to do it. More details upon request if I have time, and if you want to ask questions at the end, I can detail that part, but it's maybe too far for now. Again, the trick is to realize that since causal states are part of the properties of the physical process you observe, then if your system is described by m state parameters, then that set, whether it's embedded in infinite dimension function space, it doesn't matter. It will be at most dimension m, because that's what you need to describe your process in the end. So you can embed your distribution in an infinite dimension space. In the end, you will still get something that lies on a dimension m set, where m is the number of state parameters, which means that again, what you measure, like the geometrical properties, is an intrinsic property of the process and not of your embedding mechanism. That I may skip maybe because I'm taking too long on the theory. What we did is use a specific choice of bases here in order to encode these causal states in one reduced dimension set. And this gives you the effective state variable I shown you before. So these E1 and E2 are computed using like eigenbasis of Laplace-Beltrami operator. Conceptually, you can visualize this as kind of a PCA, but instead of maximizing the variance, you maximize the predictive information of what you observe. So dimension 1 has more predictive information, dimension 2 has more predictive information, and so on. And I will come back to that later on, that interpretation. So a recap on the theory, and then promised it's the end of the theory part, and I will go to concrete applications. If you start from an ODE or a stochastic differential equation, then these causal states are points in the parameter space. And in general, you don't have such an equation at the measured data scale. If you go back to this, you don't have a stochastic differential equation describing the evolution of, say, a forest at the scale of the forest. But that method just finds a possible representation with effective state variables at that scale, and it acts as if there was an equation capturing at least the first orders in physics of the process at that scale. Okay? So it finds such a, it tries to model the system as an SDE at the scale of the measured data. Okay, I'm going to skip this. So jumps are possible when you have finite histories and so on. Theoretically, another interesting point, now you have made this equivalence with an SDE, you have measured data up to some point here, and you have your initial causal state or distribution of at that stage, which you can estimate from data. And your model behaves like a stochastic diffusion, so it will converge the data mean as I shown on the previous example, and it will give you more and more larger and larger error bars at the end. So in a way, that's like the Fokker-Planck equation. Or you can use that Perron-Frobenius operator if you come from a dynamical system background instead of physics background. But still, what it does is it specifies how the predictive information diffuses through time until you have no more information coming from your measurement, and you have the best predictor in the long term, which is the average of your data. And going from perfect measurement and maximum information of your past to that limit is how that system describes how that transformation is made through time. Again, if you want to make analogies in physics, as in the first slide, gathering system state by information instead of energy, then that limit distribution here of causal states is equivalent to the thermodynamic limit at equilibrium, but in information space instead of energy. Yep. Examples now. Enough of the theory. So one first example, which is illustrating this, is the molecular dynamic of the N-butane molecule, that molecule here. I'm taking as inputs the positions of the atoms sampled every 200 femtoseconds, given by a colleague, Stefan Klus. And I'm using a local frame of reference so that when the molecules move in space, I'm more interested by its conformation rather than its position in space. Same exact algorithm, same code I've used before, now extracts a representation in which you have like clusters here and very fast transition between these clusters. And these trajectories, which can go back and forth between these clusters, correspond to molecular conformations. So the dihedral angle here, which is the angle between that plane, like the first 2 carbon branch, and the second 2 carbon branch, they make like an angle. And that angle corresponds to different conformations of the molecule. So that is very clear. When I superimpose that dihedral angle here on top of the clusters, that dihedral angle is not fed to the algorithm, it's just found back by the algorithm, as shown by that color scale here. Then you can dig into details and you can see that the subclusters correspond to hydrogen atom positions. I can go back to this if you want. What I find nice here is that you have a separation of timescales, which is you have slow timescale in which the system is spending some time in each of these clusters and fast transitions. So if you want to model that by timescale separation now, at a larger timescale, you would have these clusters going together and like very fast transitions through the eclipse conformation, which are much faster. Anyway, you can go from continuous to discrete here. And for physicists, it's quite important. It's like Morris-Wansink mechanism, but with clusters instead of fast slow variables. Maybe something closer to what you are interested. Here are CO2 flux and evapotranspiration data in a deciduous forest in the US, the Bartlett forest. So we are using temperature, soil humidity, sun illumination, evapotranspirations, and precipitation as measured by that tower here, the sensors at that place in the forest. So flux tower is something that measures above the canopy the amount of CO2 that goes in that, that location. 30 years of data, and what happens is you find an attractor or attractor looking here structure in which, again, you would get like the seasonal component, which is the most like the main predictor of the system. This is colored by days of the year. So you have two lobes, one lobe corresponding to winter, one lobe corresponding to summer, which are defined by the algorithm. And depending on when you are on that structure, it's a stochastic system. So you can see here clearly the stochasticity, like noise around the data. And it's already quite nice to be able to find back that structure here. But you see, yeah, like, what can we do with this? It's not really useful. Well, using another example here, so it's the same methodology, but on an experimental field in Grignan, in France. So same methodology, temperature, so humidity, and so on. And what you can see here is that in that representation, you again have the seasonal cycle popping up as the first two effective variable. So you have all the July here, all the Octobers, all the Januaries here. So now you have this system, and in that direction, which is another effective variable, you can see that three trajectories escape from the usual attractor. And I didn't know what that was, and I just computed this representation for the first time. So I asked the people managing the field, and they told me, well, it happens that these 3 years we grew corn instead of other cereals in that field. So it captures part of the phenology because simply the relationship between the environmental drivers such as temperature and precipitations, and the relationship between that and the response of the plant in CO2 is different because you have different species. So it captures causal relationship within your data and allows you to find back that reduced dimension representation in which you can make a predictive model. In the previous system here, you could get like transition for when the leaves are falling due to these two lobes and other ecology parameters, which I'm doing with my colleague Yao. But I'm not detailing that today. You can make predictions, and if you inspect the data visually, you cannot guess that these 3 years are different just based on the response of the plant. It's actually capturing something of the process you're interested in. What you are doing now in Bordeaux, I am the co-PI of an agroecology and numerics grant, one of the many grants of that program. And with Luc, who is in the room here, we are co-supervising a PhD thesis who just started, Valentine. And we are going to measure the dynamics of that ecosystem, that forest ecosystem in Ecuador, and building databases of the soil occupation, the carbon in the soil, and the biomass above the soil, and use this to model dynamics of the ecosystem. The idea would be to identify anomalies such as that here, or how much time does it take to go back to the normal behavior of the system once you have an anomaly. Not just in Ecuador, but also in other parts of the world. Oops, sorry. Like, this is a deciduous forest, but we can also make analogies in other ecosystems, like dry savanna or humid ecosystem, like a marsh. In these cases, you could quantify these anomalies, and the hope is that these anomalies correspond not just to phenology, but maybe like insects, parasites, or even if you have something which is well identified like a drought, how long does it take to go back to normal? But not just on the statistics, not just on the values you measure for, here it's water and CO2, but you could say biomass, say for example. And instead of going back to the normal and same statistics in biomass, well, maybe your system is more fragile. So you want to assert that it has gone back to the same dynamical behavior, not just the same production. Maybe that's one way to measure resilience. So it's exploratory research. We don't know what we will find, but we are going to try this kind of method on these ecosystems. We have an open position here on the method itself. So if you have like good students who would like to engage in that program, please contact us. And we also can support you for positions at Inria on that methodology if you want to apply to our group. That's possible as well. In the longer term, what we have started to do again with Luc and Pedro in Peru, at Lima, at UTEC, is we have data over these 49 watersheds here. And we try to model the global dynamic of El Niño, La Niña south oscillations over that huge coastline. So we have per watershed for each of them. We have precipitations, runoff, evapotranspiration, temperature measured. And again, it's a very, very good, excellent database produced by Pedro over many years, removing the, say, anthropic influence for dams, say, which were built at some point in time in the past 50 years and go back to natural flows of the river. So it's a very, very polished data set, 50 years of measurement of very high quality. And we also have 4 indices of sea surface temperature over the Pacific, would be like these regions here, maybe here, okay, in the Pacific, influencing the hydrology on the coast. And from that, what we get, the preliminary results are something like this. You have again the usual seasonal cycle. Here I've colored the plot from 70 to 2020. So each year corresponds roughly to one color. So the usual dynamic is in the shape of that like trumpet-like attractor here in the middle. And La Niña years correspond to the middle. And most importantly, the El Niño extreme events depart from that usual dynamic. And you can see clearly the 97, 82, and 2016 events sorted by magnitude here, departing further away for the 97, which was the strongest one, from the usual dynamic of the rest of the system. These are, again, the only first 3 components. We have information maybe in 30, 40 dimensions. So we have much, much, much more information on that. It's not just three components. That would not be enough to predict the system. And again, since we only have 3 extreme events in 50 years, you cannot make statistics on 3 events. So we have to be careful about what we can do. But it's still promising. So we are going to try to analyze what these new indicators, not just these 3, but maybe 30 or so indicators do, what they correspond to in practice. Can we relate them to known physical parameters of the answer? And what we would like to do as well is regionalize the model. That is, make localized model for each hydroclimatic consistent region. Okay, sorry. So say you have a region here which is most impacted from the most close to the equator, and both latitudinal and altitudinal influences. We have split that in regions with the same climate. And we would like to make models, say one model specifically adapted to the plains where the floods are more important, so the Niño events are more important. And in the end is where you have agriculture. The drought is more important because if you don't have water, you don't have good agriculture. So localized model are the next step. Conclusion, that's 30 minutes, so it's okay. Conclusion now, the goal of this work and global project over many years is to model complex systems and try to understand what we do by analogy with statistical physics and get a representation space in which we can describe the effective motion like an equation of motion in that effective state space. So it's quite different from usual machine learning approaches, which are all the buzz and the craze right now. Maybe we won't do as good. It doesn't matter because these things can be combined. It's different approach. It's a different purpose. We are not competing with neural nets. I mean, if you want to make predictions, obviously we are competing, but we are also doing something different. I mentioned modeling distributions with RKHS right now, but you could model them with neural nets. You could do predictions in the effective state space by modeling the trajectories with, say, reservoir computing. It doesn't matter. I mean, we are proposing something which is different, and you can plug these things at various intersections. It's just that that work is in progress, and there is so much to do, and we don't have the time to do everything at the same time, so it will take the time it takes, but eventually we'll get there, and we will merge this physics approach with machine learning approach in various ways. Anyway, all you need is heterogeneous data. You can handle pretty much all kind of data with reproducing kernels. And we only have few parameters such as the length in time of causal dependencies and the scale at which you want to measure your data, which is the scale of the kernel in that case. So characteristic scales for each data source and very few meta parameters. So again, it's completely different from the neural nets in which you have millions and billions of internal parameters. Here you just have a few of them, and that's it. Oops. Okay, and the goal would be to infer the dynamics, and one obvious application would be to get the anomalies, and these anomalies presumably have, for each system of interest, a different meaning. Say here, this is different phenology, here, these are extreme events, but maybe for other systems, you would get, again, like agroecology, you would get parasites, or you would get something that are not easy to see on your data, but that changes the dynamic itself. I'm stopping here. That's 34 minutes out of 40, so I'm keeping some time for questions.
So thanks for the talk. It's super interesting. First of all, I would like to know if you're using your own software or something that is publicly available.
The answer is both. It's my own software, which is also publicly available.
Exactly. Okay, excellent. And the other question is, if you're measuring anomalies, I guess you need a notion of a distance. Yeah. I'm guessing if you're like using a subset of a manifold and it's not very Euclidean, so how do you deal with these kind of problems?
Oh, that's the part I skipped because I didn't have the time to explain it here. It's how do you represent a distribution using reproducing kernel Hilbert spaces? And the goal is to embed distributions and conditional distributions, which are specific case of probability distribution, against specific case of functions, in a space of functions, around 2010, people like Arthur Gretton and Song and Fukumitsu and others, they just designed a way to embed distributions as points in a function space, including conditional distributions. So now you can compare two distributions with a real distance in a Hilbert space. Hence, when you do that transformation here, it's also one notion of distance. I'm using the diffusion distance with diffusion maps in that Hilbert space. So now I get a true proper measure of distance between distributions. And to answer your question for anomalies, then that point here represents one distribution, that point another one, in a reduced space and with a true distance. So yes, you can have Euclidean measures in that space.
That's beautiful. Thanks.
Yeah, thank you. Thank you for the talk. I have two questions. One is related to the anomalies that you can detect from your analysis with the reduced system, and so the discussion you have with the people on field. So how does it work, and is it easy not to have easy answers from the field saying, oh, okay, I can explain this anomaly because we used corn this year, or we had this kind of thing. And of course, you may have several reasons for the same anomaly. So how do you discriminate between them, and how do you handle that?
On a case-by-case basis. Let's be honest, at the moment, there is no principal way to relate that to knowledge in the discipline. This is a method, you have data, and it produces some variables. And it's only through fine cooperation with specialists that you can get that level of detail. And the reason is because for some cases, you already know what the anomalies correspond to, what the variables correspond to. This is the seasonal cycle because we see it. But the algorithm has no notion of season, it's just applying it to data. So it's us as humans who put interpretation on what you observe. And for some cases, the hope is that we would get new indicators, such as in the Niño case here. That global indicator, global strength, right now has no equivalent, but we discover it from data. So in some cases, you can relate that to known aspect of the discipline. And in other cases, it's just scientific discovery. You just try to dig into your data to get the new things you didn't see before, new patterns, new way to describe it. So the boundary between these two things is obviously either you know it in advance or you don't know it in advance. But the discovery aspect for me is very important as well.
Okay, thank you. Very interesting. And my second question was regarding the forecast and the prediction you can make. So how, in particular in natural processes like the ones you're talking about, how can you include some new effects, such as global warming, for example, and things like that, in the predictions you make to account for the modifications?
The theory here assumes that you are conditionally stationary. Not stationary, I mean, the statistics for observing specific events, past events or future events, that statistic can change through time. What needs to be constant is that each time you observe something, it needs to have the same consequences. But the amount of time you observe something can change. So it's not limited to a stationary process, only to conditionally stationary processes. So for climate change, the problem is that the same causes may have different consequences. Same temperature ranges may cause different something. I don't know, but that's reasonable to expect. So that method in the face of climate change might just not give any good results. We don't know. The only way to do it is to do it on a long enough sliding window. And again, that's the best you can do. But at least we escape the stationarity assumption, which is inherent to many, many, many other competing frameworks. We just need conditionally stationary, which is a bit better, but not obviously not completely good enough. So what you can do now is rebuild a model incrementally, change your distribution, your clusters, and just move through time, and just see what happens. I don't have a better answer than that. Sorry.
A very quick question regarding El Niño and La Niña cycles. We can see pretty much the extremes or the monsters El Niño that we have known and we observed with oceanographic data. But you mentioned that at the center of the oscillations, there's La Niña. What can you make of extreme La Niña events, knowing that socially, a draw can be as impactful as El Niño events on this side of the Pacific? And the other part of the question is how can we interact with the other side of the Pacific? We are trying from the oceanographic point of view to make contact and coordinate our measurements and our time series with Australia, because there is the need of englobing the whole Pacific Ocean. Can we shorten the gap of data with data processing?
I don't think you can shorten the need for that data, in the sense that here it's preliminary results on a global scale for the whole coastline, which I shown you in Peru here, okay? And obviously, your reduced dimension representation will correspond only to what you put in and the dynamic on that specific region. If you add Chile, Ecuador, and if you had Mexico, and even California, and if you had Southern Asia and Australia in the balance, you will get something which many input data, but you would get something at the global oceanic scale, but not localized to the specific region you want to. So there is a balance between how do you regionalize your model now? How do you specify the impact on that specific region, like the coastline, which is important, or the agriculture in the Andes, you said, for the drought in the Niña. And the more data you put, the more you dilute the influence of that specific thing you're interested in. So it's still an open question. We are working on that, and it will take time before we can address that question. On the one hand, you would be tempted to use as much data as you can. On the other hand, you need to specialize that to your region, and it's a tough problem. We don't know how to solve that in theory.
Especially because sometimes we need to choose the parameters we put on time series efforts, and that can determine the output that we can.
It's the case here as well. I mean,
yes,
your input parameters are characteristic scales and length of histories. So if you want to analyze your data at the scale of 5 years or the scale of 3 months, it's not the same result you get.
Yeah, sure. Thank you so much.
You're welcome.
Thank you, Nicolas. So we thank him for his intervention. And we will continue now with our first lecture of the session. We will go to water quality and the challenges therein. The lecturer will be Santiago Yepes. He's an engineer with a master's degrees in geoscience and a PhD in the same field from Toulouse in France. He is currently at the Faculty of Forestry here at the University of Concepcion, and his expertise is using hyperspectral images in the study of eutrophication processes in lakes, rivers, and such. So thank you so much for being here. with your talk about estimation of water quality parameters through a combination of deep learning and remote sensing technique applied to a lake in southern Chile.
Thank you very much. Good morning, everyone. Today, I want to share our research about the water quality using 10 series of sensor OLI that belong to the constellation Landsat 8. This I am representing to the Professor Lian Rodriguez. She's the first author, but she can come in today because they have another commitment. He asked me to present the article, our article. This is a collaboration with the different institutions, for example, the Universidad San Sebastián, University of Concepción in Inria, and the collaboration with the ERD in the France, and also the CRIAN. What is important to use the remote sensing to study the water quality in lakes today? We are used to collect information collect information using traditional methods. For example, collect in situ data is a punctual information that don't permit to have the context of the process that take place in the water body. We propose to combine this traditional method using a satellite image because this provides a holistic view that we can use the signal of the reflectant to establish relationship between the some water quality parameters and the relationship with some spectral index and band combination that we produce a retrieval model that permit obtain a view, an entire view of the different process related to the eutrophication process. Just for an idea, Chile has 1,251 rivers, almost 101 main river basins, and there are near to 375 lakes in the whole territory. In the Chilean Water Agency, only monitor 20 lakes. The idea with this research is propose the remote sensing has alternative to combine and to establish a modern monitoring system to follow the process of the eutrophication in lakes. Eutrophication is the situation was exacerbated by climate variability. For example, eutrophication is when the lake is aging with the time. Okay, it is the increase of the different variables like nitrogen and phosphorus, and that's produce the augmentation or the increase of the nutrient that promote the harmful algae blooms, okay? And the natural eutrophication is different to the anthropic eutrophication. The natural is related to the allow process, and that is affected by geological and climate factors that produce this increase on nutrients in the water body. The anthropic eutrophication is more related to the human pression, sorry, and for example, the agriculture discharge, the wastewater discharge that promotes the increase of these element, for example, the production of the nitrogen and phosphorus for the agricultural activity. This situation is promoted also for the rising of temperature, prolonged intensified thermal stratification, decline in the wind speed, and also the increase of the UV radiation. What problems are caused by eutrophication? Well, that's different process that take place in the water body. For example, the decrease of the water transparency, the accumulation of the suspended sediment concentration, bad odors, occurrence of algal blooms, oxygen depletion, that are cause of this effect in this aquatic ecosystem in detrimental of the life quality, okay? Activities related to the tourists, the biota into the water body. In this slide, we show some examples from different lakes in the southern Chile. For example, Laguna Grande, Laja Lake, and Villarrica Lake. In this year, we have different occurrence of events of algal bloom. For example, in Villarrica, with the increase of the chlorophyll A, we have the occurrence of these phenomena and with more recurrence. For this reason, it's necessary to combine the traditional measures for monitoring the lake and combine this with the satellite image to obtain or to try to fill the gaps of the database of this traditional monitoring. Try to understand the effect, for example, the tributaries to flow that flow directly into the water body. For example, in the case of the Laguna Grande, is our natural laboratory. We prove the different techniques related to the spectrometry image. We use radiometers to extract information related to the spectral profile on the surface water and try to collect at the same time information related to, for example, chlorophyll 8, turbidity, and other water quality parameters in order to establish an empirical retrieval model to transform the signal of the reflectant in the picture of the whole process that takes place in the lake. In the case of this study, we are going to study the Llanquihue Lake. It's located in the region de los Lagos. I think it's the second large lake in Chile with a surface of 170 kilometers square. I think it's one of the most deepest also lakes in the South America with an altitude of 51 meters. And there is located dominated by 4 main comunas: Puerto Varas, Frutillar, Llanquihue, and Puerto Tai. Has a high value of the landscape. It is very important for the tourists in the region. Okay, the lake also is fed by several tributaries. For example, the Maullín and Petrohue rivers, which flow into the lake from the east and west. The most of Llanquihue Lake is the Maullín River that flows directly in the Pacific Ocean. With respect to the methodology, we use a different approach of deep learning techniques to predict the behavior of the fluctuation of different data sets. For example, we apply time series from 1999 and 2021 using information related to the in-situ data, meteorological data, and satellite data. And we apply different models, for example, the SARIMAX, the long short-term memory, the recurrent neural network. The idea is try to test different case ABC using the variables alone, and then we combine in different iteration. SARIMAX is a seasonal autoregressive integrate moving average with exogenous regressor. He used the processor ARIMA, the model ARIMA, is considering both seasonally and exogenous variables. Is very useful for the time series model. For the other hand, we have the long short-term memory, the last TN, is similar to the recurrent neural network traditional, but in this case, he has a cell that has 4 gates: input, forget, control, and output. And the forget is very useful because he permits the scarce information during the evaluation of different fluctuation in the analysis. At the end, we had recurrent neural network. This model is suitable also for the use in time series of data. Well, I'm going to show you some linkology parameters that we use in the model. For example, we combine information related to time series of chlorophyll 8, transparency, total nitrogen, temperature, and also total phosphorus was included into the model has this in situ data. The idea is, I'm not sure, I don't know the detail exactly if Lien use information related to the species in the lake. But she combined information related to the meteorological data. For example, she used different parameters like temperature, wind speed, relative humidity, cloud cover, accumulated precipitation, and also radiation. This combined also with time series of satellite images from the sensor only. When he download this image, it was necessary to pre-processing in order to calibrate radiometric and atmospheric the image, the scene. In this case, we apply the model Acolyte. This is very special for the continental waters because it's possible to mitigate the effect of the sun glint in the water. It's a kind of reflection on the water surface. It's very important to establish relationship between the signal of reflectance and the in situ data. We also evaluate the different of day between the acquisition of the image and the collector of the data. In this case, in this feature, in this slide, I show the relative importance of different parameters, not only the meteorological data or the linkological parameters. We combine this information with a spectral index, band combination that are sensitive to characterize the relationship with the chlorophyll A, okay? And this is a kind of sensitivity model that permit to understand what variables are more important to include into the model. And we test different combinations. For example, in the first, we apply the 3 methods. The blue line is the real observation. Red line is SARIMAX. Green line is LSTM. And the purple is the recurrent neural network. And we can see the relationship between the nitrogen, phosphorus, silicon, the sulfur, oxygen, temperature, conductivity, and transparency. This is only the first iteration with only the in situ variables. The prediction was satisfactory, but then we combine this information with meteorological variables. we improve the performance of the retrieval of this variable. And at the end, we combine in a third test using the information from the satellite image. I mean the spectral bands alone, and also the spectral indices that are very sensitive, has an NDVI or phi. And we prove that, for example, the model LSTM has the best performance to estimate this kind of variable. As conclusion, we have that the combined techniques of remote sensing and machine learning and deep learning has proved to be valuable for the estimation of the water quality parameters, such as chlorophyll A, the coefficient of determination value ranging from 0.64 and 0.93 from the model LSTM, showing that best performance in any of the case tests. Of the three cases applied in this study, case C, when we use all variables integrate, showed the best result for our station in the lake. Traditional monitoring methods face great complexity during autumn and winter season due to the characteristics of this season. For this reason, we propose this methodology as an alternative to recover model to predict information related to the water quality parameters as chlorophyll A or turbidity. Well, in the perspective in the future, we planning to combine this in analysis with the altimetry, satellite altimetry, and our intention is combine also with another constellation, for example, Landsat 9, and also the information from the satellite from the program Copernicus, Sentinel-2, sorry. And the idea is to apply to collect information also in situ related to the radiometry. The spectral signature of the water permit to understand better the condition, the physical and chemical condition of the water body, and we can be again capable to create a proper index to understand some water quality parameters. For this reason, we are going to plan it to combine quantity, quality, and also to understand the climate variability in this place. This is support for the project from the seed. It's called seasonal and interannual variabilities of inherent and apparent optical properties in lakes and reservoir in the south-central Chile. Implication for biooptical modeling and water quality. The idea in the future is we are using the Laguna Grande has a natural laboratory. The idea, for example, is prove different methods related to the atmospheric correction. Because the effect that I told you before, the Songling effect, is like a mask when I try to establish this relation between the reflectance signal and the in situ data. And for example, in this case, we prove for the OLI sensor different methods of atmospheric correction. For example, Acolyte, ECOR, and LARS, and other methods relate to the atmospheric correction for continental water. And we prove that Acolyte has the best performance to retrieve the information of the chlorophyll A in Laguna Grande. We use also también an approach of bootstrapping to obtain a more robust estimation of this parameter. The next step is try to use a high spectral cameras to combine the information of the continuum of the electromagnetic spectrum in order to obtain more detail about the process of the eutrophication in the lake. Thank you very much. Sorry, if you want more detail about the technical aspect, maybe it's better if you write directly to Lien. Okay.
Thank you. Anybody else want questions for our speaker? No?
Okay, I have a non-technical question.
Okay.
You mentioned at the beginning that 20 lakes were under the supervision of the national agency.
Yes, only 20 lakes.
That's my question. Why only 20?
Because sometimes it's the cost and time is very high, and I don't. Sometimes the Chilean water agency don't have the enough resource, human and the cost to monitoring this. Not only the lakes, the river also is very important. No, don't have the resource for this work.
And these lakes are public, they are not private.
Yes, the lakes are public.
Okay.
Yes. Okay.
But how do you prioritize? I know that Laguna Grande is an excellent natural laboratory because of the proximity and all the possibilities of observation. But in lakes like Villarrica and other high altitude lakes, the variability can be, the seasonal variability and the environmental variability can be stronger. And the anthropogenic pressure on the lake you are observing can be, also very different. How do you prioritize, other than proximity, which lakes would be, for instance, a good suggestion for monitoring to the entities here in Chile?
Thank you for the question. The selection of the lake is related to the project from the sea. We study different lakes in different trophic conditions, and we select the Villarrica and Yanquihue because in the last year they are changing the trophic condition related to the land use change, related to the activity of the agriculture that promote the wastewater discharge into the lake, that promote this process of the eutrophication in the lake. The other lake that we study will be La Nalhue Lake. This is affecting also for the land use change in surrounding the shore of the lake.
Okay, thank you. Thank you so much. And we will go now. There is a question from the people who's watching online. Okay. Let me see. Okay, so the question is, so says Luis, thank you for your talk. Regarding the variables in your study, was the amount of satellite data and in situ measurement constant, or did it vary? In case of different number of measurement, how did you ensure an uninformed number of measurements for each site studied?
Well, you need to collect information on different seasons of the year. It's very important. The number of in situ data is considering the surface of the lake, and also we acquire information of the satellite image, and we build a spectral index to understand the variability of these chains. And using this information, we select different locations to extract the water sample. but I don't have the number exactly to say. It's not the same Yanquihue or Laguna Grande. Okay?
No more questions online or physical. So thank you so much again for your talk. We will welcome now Katia Aitameur. She's a postdoctoral researcher at the Inria Center at the Université de Côte d'Azur in France. She is working on the Lemon project in Inria. Katia is going to walk us through time parallel algorithm for multi-step schemes. Thank you.
Thank you for the introduction. So my name is Katia Itamer. I work as a postdoc in the Lemon team, and this project is also in collaboration with Inria Chile. So this postdoc is supported by the International Relations Direction of Inria that you may have heard about during the week. And so this project just started a month ago. So today I will talk to you about a work I started during my PhD that is related to time parallel algorithms. So during my PhD, I was working in the French Commission of Nuclear Energy, CEA, and I was also working at Sorbonne University. And this work is in collaboration with my advisors for my PhD, Yvon Madé and Marc Tajkman. So today I will introduce you the family of methods I've been working on for reducing the computational cost of time-dependent problem. And then I will present you in details the algorithm we are working on, which is named parallel method. And then I will explain you how we adapt this parallel method to the software that is developed in CEA and that is dedicated to nuclear safety studies. So in this work, we are interested in a very generic problem. We want to solve this equation where u is the unknown and it depends on the space variable x and on a t variable, time. X lies in a space variable omega that I call omega here, and t goes from 0 to a final time. So we equipped this problem with an initial condition and a boundary and some boundary conditions. So one family of methods that have been developed for reducing the computational cost for the solution of this problem. One first family is domain decomposition method in space. So the principle is to split our space domain omega into subdomains and to assign sub-problems to each subdomain. These problems can be solved independently, and the key ingredient of this method will be to choose the right condition at the interface to communicate between subdomains. So this kind of space domain decomposition allow to reduce the computational cost when we want to solve this equation with a numerical method. And the typical behavior we see is the one here in this figure. Here we plot the speed up when the number of processor is growing. So the ideal speed up we would like to have when we do parallelization is that when I use n processors, I want to divide the overall computational cost by n. So space domain decomposition allowed to be very close to this ideal speedup until reaching some plateau. This plateau is reached when we split too much our space domain. So we spend more time communicating between subdomains than really solving the sub-problems. So this is where the second family of method appears, the time domain decomposition methods. This strategy was proposed to as a complement if a first strategy reaches its limit. So just like here, if we couple the time parallel strategy to the space domain decomposition, it allows to get closer to the ideal speedup after reaching the plateau. So in this work, I will mainly talk about time parallel methods, and I will talk about one specific method, which is called parareal. I know this word seems strange a little bit, but it is a nickname for parallel method for real-time simulations. So I hope you will get used to this word. You will hear it many times on the talk. So these two family of methods are very generic. It can be applied to any problem. And in the context of my PhD, I used it on a specific context. So in this collaboration with CEA, we worked on nuclear safety, a software that is dedicated to nuclear safety studies. This software is called Qatar, and it is mainly used to simulate two-phase flows within the cooling system of the reactor. And these simulations allow to see what happens in the reactor on accidental scenario and to validate all the emergency procedures that are used in real life. This software has been developed in a very precise goal. This software was developed to represent the whole nuclear power plant. The point here is not to make very fine simulations with millions of cells for the mesh, but the main objective was to make some simulation at the system scale. So for that, they chooses to make simulation with a very coarse mesh in order to represent the whole geometry. So when I arrived in this lab, there was already space domain decomposition implemented in the software that reaches its limits. Since we don't have a lot of mesh cells, the space domain decomposition is not very efficient. And we wanted to test if the time domain decomposition can help improving the speed up performance. So in the sequel, I will present you in details the algorithm we adapted to this software, which is called parareal. And this parareal algorithm was introduced about 20 years ago by these authors. So let's go back to our equation. Here I dropped the dependency on X, and I only have a system of equations, a system of ODEs. So if I forget the parallelization, what I would do to solve this problem is to choose one time scheme, for example, explicit Euler, and I will compute the solution at each time step here in a sequential way until the final time. And this process is sequential by nature because I need to know the solution at Tn to compute the solution at Tn plus 1. So what's the idea of parallelizing this process? So first of all, we split the full time interval into time windows, just like that. And then we choose two time schemes. The first one will be called G. G will give a coarse approximation of the solution, but will have a negligible computational cost. So in my parallel algorithm, I can use it in a sequential way because its cost will be negligible. And the second time scheme, I will denote it F, will give an accurate approximation, but its cost will be way more expensive. The idea is that F will never be used in a sequential way, but always in a parallel way. So now that I have fixed these two ingredients, we can start initializing the algorithm. So at k equal to 0, we only use the coarse time scheme. It will give us some initial guesses at the beginning of each time window. And then I move to my first parallel iteration. So starting from these past initial guesses, I can run in parallel some fine approximations. After that, we have a prediction step where we will use again the time scheme G. So we start with T0. It gives us this point. And we apply a correction at T1, combining coarse and fine approximations. And we go on, we propagate again this correction and apply an update for the initial condition at T2. So we can see now all these new red dots. These are my new initial conditions to each time window. We see that it didn't reach my target solution in dotted line. So I will need one more iteration to find my target solution. But here is the spirit of the method. So now how to adapt this parallel method to industrial software. The first step, it was to understand the time discretization that is used in the software. So this is where multi-step time scheme appear. What is a multi-step time scheme? It is a scheme where for computing the solution at Tn plus 1, I need a set of values in the past. For example, the solution at Tn minus 1, at Tn minus 2, etc. And for this software, there is a two-step time scheme implemented. So we needed to adapt the parallel method to this discretization. The other condition we want to fulfill is to build something that is non-intrusive, which means that we don't want to modify anything on the industrial software. We only want to adapt the parallel method to it. And also, we want to preserve all the properties of the original method that will be useful for our work. For example, we want to preserve the same computational costs. We want to preserve the same convergence properties because this original method converge fastly to the target solution. And also we want to preserve a kind of consistency property. And at the end, we also want to run it on some test cases that are relevant for CEA. Okay, so I will start with the first step of this work, which was adapting the parallel method to the time scheme. So what is the problem when we use a multi-step time scheme? Imagine you are at T2 and you want to begin your fine approximation with a multi-step time scheme. You will need to know some solutions in the past, but the algorithm is built in order to solve the problems independently. So we have to define these quantities, and we have to define it in a good way to avoid generating additional errors. So this is what we do. We define some new quantities that will help us initialize the multi-step time scheme in T2, T3. And that's it. So we built our multi-step parallel method that is non-intrusive in the fine and the coarse time schemes. This method can be generalized easily to any multi-step time scheme, since here I can apply this translation to every point of the trajectory. Also, we preserved the same computational cost of the methods, and we preserved the same theoretical properties. So now I will move to some numerical results to see if this nice algorithm in the paper works in real life. So one naive test, one first naive test, it is on a system of ODs that simulate chemical reactions. So this is called the Bruxellator system. In this test case, we fix the parameters of the ODs in order to be in a stiff regime, and we test the ability of the multi-steps method to reduce the computational costs of this problem. So we choose our parameters, the solver G, the solver F. We split the full time interval into 180 time windows, and we run the multi-step parallel method. So what we see here is the evolution of the error across the iterations of the algorithm. In blue, we have the error between the parallel solution and the target solution. In blue here, we have the error made by the multi-step adaptation that I had just introduced to you. And in red, we have the original method that makes an error initialization at each time window and each iteration. So as you can see, if we make a naive initialization, we won't converge to the target solution, and this error will just stay constant across the iterations. Now that we made our naive test case, we can move slowly to the real-life application. One intermediate step before plugging the parallel method to the industrial software, it was to implement a numerical clone of the software. So we developed a library that reproduced the model and the discretization of the industrial software on a simple test case. So in this small library, we don't have all the options available in the software, but we have like a few terms to simulate a family of test cases. So one test case we can simulate with this library is this one. Here we have a closed system. Here it should be closed. And we have air and liquid. So we initialize the system at disequilibrium, and what we are waiting to see, it is these two interfaces that will oscillate between two positions in the two branches. So this is already a relevant test case for the applications of CEA, because here we test, we are in a configuration that is difficult for two-phase flows. Since here we will have purely air and purely liquid. So for the two-phase flows, it is a little bit difficult to simulate this kind of configuration. Okay, so now we apply the parallel method. We choose some parameters of the method, and we compute the speed up that we obtain. So we make some tests from 5 to 70 processors, and we increase the number of processors of 5. So until 25 processors, it increases slowly. And then starting from that, we see two trends. So we either have some performance about 3.5 or 3.5. And we also have all these points that are around 2. So what we see here, it is one limitation of the parallel method, because we know that the speed up we can have with this method is depend on the number of iterations we made. For all these points, we converge after 2 iterations, and all these points, it's after 3 iterations. So the upper bound, exactly what is the upper bound we have with the speed up? It is bounded by this quantity where n is the name of is the number of time windows, and k is the number of iterations that we make until convergence. So the more iterations you will make, you will get further than from the ideal speed up that is equal to n. Okay, so that was the first test before plugging the parallel method to the industrial software. It was quite encouraging, because in our numerical clone, we don't have all the options that are implemented in the industrial software. And also we know that time domain decomposition is here as a complement for a first parallelization strategy. So for sure, if I only use time parallel method, this is not very efficient to have this kind of speed up, but time domain decomposition arrives when the first strategy reaches its limit. So after this test, we developed a library that contains the parallel method. And we developed it in order to use the industrial software as a black box. So all the corrections of the method was implemented in the library, and the software was only giving us coarse and fine approximations, and the rest of the algorithm was in the library. So for example, the Qatar code was giving the initial guesses at each time window, and then here we were making our corrections, and after the update of the initial guesses, we send it to the industrial software with the instructions, which are the time steps. It can be coarse or fine. The time subinterval, it can be one in the middle of the time interval or at the beginning. So this is how we decided to test this method for the industrial software. So one small comment about this library. So we treated just one part of the data given by the industrial software, which are the main physical unknowns here, like the pressure, the velocities of each phase. And because this code will furnish a lot of variables that are relevant for post-processing, for example, but us, we were interested only on the physical values that are the unknowns of the model. So now I'm going to show you one result that we obtained during my PhD that is the most real-life application I did. So in this example, we have a reduced geometry that is made of reactor core and a part of the primary circuit. So what will happen in this test case? At the beginning, we will have only liquid everywhere, and a breach will occur somewhere in the primary circuit. This will cause a decrease of the pressure inside of the reactor core. The temperature will rise a lot, and all the liquid will be steam at the end of the simulation. So this is a very useful test case for the nuclear energy engineers. And we tested our multi-step parallel method on this. So here we see one result. We split the full time interval into 5 time windows. In red here we see the error after the initialization, which is the error of the course time scheme. After one iteration, the error is reduced here in blue, but we didn't reach the target accuracy here in a dotted line. And after one more iteration, we are satisfied with the result. So what does it mean if we look at the physical variables? Here we plot the volume fraction of the vapor. This volume fraction is between 0 and 1. At the beginning, we have no vapor in the system, so it is 0 at t equal to 0. When the breach appears, we will have a creation of steam, and at the end of the simulation, it will be only vapor inside of the reactor. So here in this plot in the middle, we see the solution after one iteration, and we see that we have some jumps here between 2 times sub-window. So we need one more iteration to have a good profile for the volume fraction. So this ends the numerical results part. I will finish to resume a little bit. Here I told you how we adapted a parallel algorithm that seems a little bit abstract for an industrial software. The first step was to understand the time discretization of the software and to see how to adapt the parallel method to this time scheme without touching anything on the industrial software. So we made some analysis of this new method we proposed to see if we didn't get too far away from the original method. And we tested it on a relevant test case for the nuclear energy community. So I will finish on some messages. I hope I convinced you that parallelization in time is good is a good option as a second strategy if your first strategy is reaching its limit. It also has a very generic formulation, and it can be applied to any time-dependent problem. Maybe you will have to adapt it to the time discretization, but it's feasible. And I would like to conclude on one example that makes the link with between time parallel method and neural networks. So there is this recent work that uses the parallel algorithm to reduce the computational cost of the training stage for physics-informed neural networks. So the two strategies seems to be compatible. Yes. Thank you.
Thank you, Katja. We are a little bit short of time. Is there any question online? No. A quick question in the audience before going to our coffee break? No? Then we can just go for coffee and we can discuss with Katja in this very interesting subject. We'll reconvene at 35. Bueno, vamos a retomar. Estamos un poquito atrasados. Me parece que el café estuvo muy bueno y muy buena la conversación, lo cual es súper. Vamos a invitar ahora entonces a Mauricio Sepúlveda, que es nuestro próximo lecturer. Mauricio es profesor de la Universidad de Concepción desde 1996 y su especialidad está en las Applied Mathematics. Él nos va a hablar ahora de Inverse Problem for Conservation Laws Modeling Various Cell Biology Processes. Mauricio es un colaborador de largo término de Inria y ha participado en proyectos como Anaconda, que ha sido emblemático para el instituto. Así que muchas gracias, Mauricio.
Okay, thank you very much. Okay, thank you very much for the invitation to this very nice Journées Scientifiques of Inria. My connection with Inria this year is it is very important because I collaborate with some French people in a long stay in France this year, and the work that I present is an inverse problem for some biological model, in particular in some intestinal crypt that I talk here. The intestinal crypt model is a model who is interested some people of the Inria and the INRAE laboratory, who is in Jouy-en-Josas, and they study a lot of biological model, and this is one of them. And they study the evolution of the cells in the intestinal part of some mammals, and in particular, the intestine is formed by some crypt, and we model the evolution of these cells. And I talk about some inverse problems and the techniques, the numerical approximation, and other problems that we are interested with the teams. Now the people and the projects. Okay, the people that which I work in this project is first Béatrice Laroche and Marie Hagebert, both of the INRAE that I know. Marie is a student of Béatrice Laroche. She's a PhD student, and she finished now in December about the model of the intestinal crypt. And the other people is Frédéric Clément, which is the head of the Anaconda project, and the teams Musca Inria, and Romain Binek, who work in the INRAE of Tours, and now he take a sabbatic in the United States. And this is the project who support this work. First is the teams, the INRIA teams, Musca, which is the sigils, and the Anaconda is a project associated to these teams, Musca, where there is a lot of people of Paris-Saclay, of Université d'Orléans. In Concepcion here, there is Luis Miguel Villada and me. And of course, Inria Chile is related to this Anaconda project. And other projects, for example, the program Jean Alembert, who support me for the long stay in France, and the ECOS project, which is related in the research with the Anaconda project. Then the models. the models of the evolution cells is there is the intestine, the intestine where the nutrients are processed, are formed by some crypt, microscopic crypt of 200 of microns by 500, no, 200 by 50 microns, where there is 100 of cells, and these cells are divided and differentiated and increase in the evolution of their life. And there is 5 kinds of cells in this in one crypt, for example, and they start with the stem cells. The stem cells produce or are differentiated and divided in the progenitor cells, and the progenitor cells produce the enterocyte cell and the goblet cells. The enterocyte cells are charged to process the nutrients who arrive to the intestine, and the goblet cell produce some mucus who help the enterocyte cells to this process of absorb the nutrients. And there is a fifth kind of cell called DCS, which is the deep crypt secretory cells who help the stem cells to divide it and produce more stem cells. This is the description of the crypt, and the crypt he have a form which is very small in the depth and like a tube of laboratory. Then the equation are by modelization of this process of evolution cells using a piecewise deterministic Markov process, arrived to this partial differential equation with non-local term. This is the modelization of this guy in this paper, Leo Darrigade and Marie Hagebert and the other peoples. He worked in this, and this is the general model. We have a convective term which depends of the interactions between, we describe the repulsive force. The right-hand side of the equation describe the division and the differentiation of the cells. And this equation, which is a little complicated and there is a little unstable numerically, are approximated by other equation. This is the crypt geometry. Here there is a function Vz, which describes the geometry of the crypt, and he have the property who have null in the depth of the crypt and in the bottom of the crypt and in the top of the crypt. And by approximation, we arrive to this equation, which is more standard with non-local terms, but with by approximation, we arrive to a diffusive term, but it's a diffusion with a degeneration given by the phi z, and there is some cross diffusion terms given by this rho L dz rho, which this rho term is the sum of all the cells. It's the total of the cells, included all the cells, and rho L is each one of the cells. Then when I multiply these terms and include it in this derivative, we have a kind of cross diffusion, and it's non-typical cross-diffusion, but it's a little hard to simulate. And the right-hand side is the nonlinear term who describes the interaction between the different type of cells. We suppose Dirichlet condition, boundary condition at the bottom of the cells, and Neumann null flux in the top of the cells, in the top of the crypt. Then for simplification, I suppose only 3 kind of cells. No, I exclude the heterocyte and the globulet cells for simplification for the inverse problems. And we consider the stem cells and the progenitor cells given in this model. The total cells are the sums of this, and the rho is the sum of the stem cells and the progenitor cells. Then the equation can be reduced to this system of 2 equations. And this is an example of model with these 2 kind of cells, including these DCS cells, which is in violet. The green curve is the phi z, which degenerate in 0 in the top and the bottom. And red is the stem cells, and the yellow is the progenitor cells. And this is a simulation given by my colleague, which include all the 6 the 5 kinds of cells, with the total cells here in black is the sum of the cells. And we see that yes, the stem cell of the progenitor cell are in the bottom, and the enterocyte and the goblet cell are to the top of the crypt. Then one inverse problem who are interested by my colleague and the community of the people who study this kind of model is to identify some parameters who are unknown in the model, or very known, using some observation or experimental data. And one of interesting parameter who intervene, who act in the evolution of the cells, is the function of the density of the DCS cells, which is not well known. They know that there is in the bottom of the crypt, and is very important to the shape of the stem cell who impact on the other cells. Then to identify the shapes of this rho DCS, it is an interesting problem for the inverse problem. Then the idea is we have some observation, for example, of the stem cells and the total cells or the progenitor cells, and we define a cost function, which is the distance between the simulated cells and the observation in norm L2, for example, and to minimize this cost function and find the parameter which adjust, which find the better solution in relation to the observation. Then the inverse problem is a kind of optimization, it's a minimization problem with some restriction. This is the cost function, this is the form of the cost function, and we give that there is a kind of convex shape in terms of 2 parameters that I chose, These two parameters is the position and the level of the density of the disease cells. Then we define some a kind of weak solution. This is the equation multiplied by some test function for the two equation in the system. And because I want to minimize a cost function, we define a Lagrangian, and we derive the Lagrangian respect of the variable rho and rho SS. And in order to find a critical point of the Lagrangian and to obtain the minimum. Then nulling the Lagrangian give some adjoint problem. The adjoint problem is the test function who verify this equation, which is a backward equation, with final solution and with boundary condition and with some coefficient which depend of the direct problem. And this is the system. It's linear, but it's not easy because there is a lot of interaction. It's very couplet system. And with the generate term, because the phi z are included also in this equation. Then an optimally necessary condition of criterion is to compute the gradient, and the gradient is possible to compute by some calculation in terms of the direct problem and the adjoint scheme and the adjoint problem. And this is the expression, the explicit expression for the gradient of this cost function in terms of the parameter who want to identify. Then we want to apply a numerical approximation. One possibility is to use the finite volume method because there is a conservation laws here. But my colleagues see that the BGCAC scheme based in the finite volume method is better to the instability of the system because this very strange cross diffusion and the regenerate diffusion terms. Then this BGCAC scheme is a very nice scheme, but is a kind of finite volume with a lot of terms described in terms of Maxwellians and also. Then one question to pose is what we do, the discrete of the adjoint problem or to find the adjoint scheme to associate it to the direct problem. We prefer the second possibility because the BGCAC scheme is very hard, and to take this to obtain an adjoint scheme for that and to process the gradient. Then the BGCAC scheme is described, but it is kind of finite volume. It's not the standard finite volume, but it is kind of finite volume. We approximate the solution that we want. There is we have some numerical flux here on the right-hand side, and the numerical flux is expressed in 4 terms, which is associated to the BGCAC scheme. Then this is the election for the numerical flux, the second order scheme, and we derive. This is we derive the adjoint scheme associated to BGCAC scheme by the similar method. We define the weak formulation for the numerical scheme, and we derive this the Lagrangian in terms of the weak solution and the cost function in terms of the unknowns, and we obtain some gradient. This is the cost function, the Lagrangian, which is the cost function, plus weak formulation. We have an adjoint scheme associated to the BGK scheme, which is that there is a lot of derivative in terms of the numerical flux in terms of some Maxwellian, and the derivative of the Maxwellian is in terms of the unknowns row. And we have these numerical schemes of transportation equation. Then finally, the derivative of the cost function can be computed, and we obtain this expression for the compute of the derivative, and we have some result of parameter identification. We start with, we don't have a real observation. We want to some real observation, but we simulate the algorithm of this described here using an observation which is a simulation by standard DSCS, and we start without DCS. Then the parameters are 0, and we try to reproduce the DSCS solution, and we converge in 17 iteration of the gradient and 72 evaluation of the cost function, and this is the evaluation of the cost function is very close to the observation, starting by this point, and this is the result of the parameter identification. Now, by times, I don't talk about the other problems, but in works that is, with Romani Vinic and Frédéric Clément, we are interested also in other models of the ovogenesis model and the adipocyte model. Then there is a lot of technical description of this, but I don't work about this, but it is other model which are transport equation with non-local term and non-linear the diffusive term. This is, for example, the model of the adipocyte cells, which is a transport diffusion equation with non-linear and non-local terms. And we are interested, this is some solution, and we are interested to identify this kind of parameter who act in the non-linear and the non-local terms. The ovogenesis model is another model of the eggs of fish, and there is a transport equation in times and age of time of and dimension and diameter of the eggs, and we have a non-local and non-linear transport term here. The non-local transport have this form, and the non-linear transport have this form, and we try to. The idea is to identify these parameters, but it is in work. And now this is the biography. There is a lot of work here. The forest about the talk that I present here about the inverse problem for the crypt, the intestinal crypt. And there is an interesting work here that I don't talk, but the fifth is Luis Miguel Villada, who worked in the Anaconda project also, and with Nicolas Torres, who he's an ex-student. We work in some neural network, and we are interested also in some inverse problem for this kind of problem for the neural networks that we are interested in that. And this is my presentation. Thank you very much.
Okay, so what type of real observations you need to test your model?
Okay, it is possible to obtain. My colleague who work in the Inria of there is some observation, but they work to obtain this observation. They cup the intestine, and they see they can distinguish the different kind of cells in the crypt in some in a fixed time when.
So you cannot use non-invasive methods like MRI or
For live mammals for live no yes
no.
there is
Okay.
the experiment only in
Can you go back to the first equation that you showed, where you introduced the rho and phi and w, please? So is rho the density of the cells?
Yes. Rho is this equation or the first?
Yeah, that's fine.
Yes.
It's fine. So rho is the density of each cell
Of
species.
each cell, of each 5 cell. L described the stem cell, progenitor cells,
Right.
etc.
And phi is, what is phi? Phi of z.
Phi of z is describe the geometry of the crypt.
Oh, okay, yeah. That's
Which is 0 in the bottom and 0 in the top.
and then z is the spatial coordinate.
Yes.
All right. All right. Thank you.
The next presenter is me. This is a little bit odd. I'm going to present to you the least equational presentation probably from the whole symposium of Inria. I changed the title a little bit because it's symbolic also how oceanography is adapting to artificial intelligence and data science in general. And I will explain to you why that is. Also, we have challenges that are critical and important right now. We are in one of the disciplines that are in the front line of climate change, and therefore, people, the users, need answers from us. And they are actually actively demanded that we seek not only to explain how the natural world works, but also to have some sort of solution for everyday life and everyday adaptation. So that's why this is called We All Want to Adapt. I'm going to present to you the center that I'm leading now. It's COPAS Center, the Center for Oceanographic Research in the Eastern South Pacific. And it's a center that has 20 years of experience. It means 20 years of gathering data of all sorts, and now we are in the process of creating some sort of solutions and approximations to learning how data can actually help us predict what will come out of climate change for the ocean. So some things are in the works, some things are working, and definitely some things are in our future. And my objective right now is just to show it to you. I very much like to do analogy in my talks in order to explain how we see the world. And this is why I mean by this is really not any equation is going to appear in this talk. So let's keep in mind that we work in natural environments, right? And the whole session has been around describing and explaining how the natural world works. But if you go to the forest, you will see this. And you will see as much processes as you will see components of the natural environment. You will see variables, you will see parameters, living things, inert things, degrading things, and cycles and processes. Nutrients being degraded and utilized by living organisms, fluxes, greenhouse gases being produced and consumed. The same is in the ocean. Only when you look at the forest, you can actually see where it ends. And you have, this spatial connection to the environment that you're working on, and you know exactly where to put your sensors and your towers for humidity, turbidity, cloud coverage, and such. But for us, when you are looking at a time series that comes from oceanographic data, it's like looking eternally to the same spot, to the same tree, among the whole forest. So how do you reconcile the fact that you are perpetually looking at the same tree for years and years, and the need to cover the whole thing, especially when it looks like this, And this is really how we go gather data. So a day in the office can very much be something as rough as this, or the tropics, but I personally don't like much the working on the tropics. I am really a rough sea person. So how do you reconcile looking at the same spot forever and ever, having time series, and the need to cover space and time? So this is one of the main challenges for us. The idea for us, obviously, is to observe not only the surface of the ocean, but the thousands of meters, below. So it's a spatial and temporal integration, and I'm sure you all pretty much understand this. We tackle from space certain parameters, as we saw with the approximation of pigments in lakes. We are able to describe pigments and color of the ocean pretty much, and extrapolate to primer production, carbon fixation, CO2 integration into the water column. That's pretty much something that we are covered. Although in certain areas of the ocean, such as the South Pacific and the Austral Ocean, it's pretty difficult because of coverage of clouds. So satellites are not always an option for us in that department. The other thing is in situ observation, of course, and we are facing the one single tree problem, in that department. And the other one is, of course, modeling. And our main objective as a center is to come to this, to be able to observe the ocean, gather data, process it, translate it into something, and get it back to the user. And the next few minutes, I'm going to just talk to you about 3 examples of how we are dealing with this and try to achieve this. But first, the protagonist of the whole thing. I have been talking about greenhouse gases that come in and out of the ocean. We all know, or probably not all, but believe me, the ocean respires a lot of greenhouse gases. For us, it actually acts like a mitigator for climate change naturally because of its capacity of produce enormous amounts of oxygen, absorb enormous amount of CO2, but also storage enormous amount of heat from the atmosphere. So part of this is done by these kind of creatures. Microscopic plankton components that actually account for pretty much 80% of the biomass of the whole ocean. Here in Chile, these are particularly important because, along with Peru, we can sustain 10% of the global fisheries. And that is because the existence of these little guys. So this is a particular kind of plankton, coccolithophorids, which are prone to acidification because they are made of carbon calcium. These aren't. These are made of glass, of silica. These are diatoms. This is the microphytoplankton. And this is what actually, for a biogeochemist like me, the ocean looks like. It looks like this. A lot of, rough seas and microbes. Microbes translate to nutrient cycles, which translate to fluxes of heat, greenhouse gases, and carbon, which is also the Bitcoin of climate change studies. So modeling studies applied to climate change in the IPCC right now are talking about, well, what is going to happen with the ocean without oxygen? Deoxygenation is one of the major problems we are facing. Oxygen minimum zones, meaning enormous water masses with hypoxic conditions, not very suitable for oxygenated life. Therefore, photosynthesis is kind of out of the question for those kind of environments. And simulations are particularly keen on explaining what will happen with the ocean in a world with less oxygen and what eventually will happen to us in that kind of environment. But the thing is that without an understanding of microbes and how they work and how they respond to environmental conditions and changes, is a very difficult scenario for a modeler to explain what will happen. I recently was talking to a colleague of mine that was trying to explain the fact that in a world without oxygen, probably in 300 years, microbes will take the lead and they will produce oxygen again, and therefore we will be super awesomely adapt to climate change. But that's a very bold statement to do, and it's a very difficult thing to explain to the public. You cannot go there and say, hey, it's going to be okay because in 300 years, oxygen will appear again, the model says. But the model needs to figure this out beforehand, before talking to the audience. So this is our vision of the world, and this is how we are trying to get to solutions to the everyday life, with questions such as, is the ocean getting more acid, toxic, oxygenated, deoxygenated, and such? So we are getting somewhere in areas such as hubs. And this is the work of Caterina Alves de Souza, a young researcher that is going to join Universidad de Concepción in a few months. She's been working on the chemical aspects of harmful algal blooms, toxins expelled by certain kinds of plankton, like the ones that I showed you, that has social consequences for fishermen, but not only fishermen, but people in general, because if you actually ingest it, you will probably get paralyzed or even die. In 2016, during one of the extreme El Niños that we saw early in one of the presentations, we had a very strong response in the ocean with the proliferation of extended blooms in the northern Patagonia, in the whole area of northern Patagonia, that resulted in social unrest. So in countries like Chile and many others, environmental conditions determine the proximity of social conflict because it relies on, the living of society. So for a long time now, the detection of such toxins, which are diverse and can interact with each other, depending on testing of mouse. So if the mouse dies, therefore, there is something to worry about. But there's no need to explain how that is wrong, in so many levels. So we came up with a solution, one of which is the detection of cells directly using a submersible cytobot, which is a cytometer that actually scans the water and continuously take pictures of different things. It can be plastic, it can be mucus, it can be cells, living or dead. And the exercise that needs to be done and that was done is to teach the data to recognize different shapes, forms, and substances in 3D approximations to identify in a continuous basis, in a real time, using machine learning, these kind of cells, and to differentiate the ones that are cool from the ones that are not, and establish early warning systems. So using that particular technology now, we are able to translate into genetic material sequences, shapes, forms, colors, and such, to translate it into a very simple model that can be available in your phone, in real time, and detect conditions favorable for blooms, but also when the cells and toxins are already there, the combination for which you need to take measures. So this is a project that the Alison Asturias laboratory has been working on, and we are near completion of this, and we are very proud of it, because it's the first time that using a time series, meaning that you are looking at the same tree, you can actually teach the tree to give you some information. And the combination of in situ data with predictive modeling can actually translate into something that in everyday life can maybe avoid some conflicts and some social unrest and some sanitary conditions. We are also applying our observations to port management. And this is also one other challenge that we are working on. This is a project funded by ANID, which is called a public challenge. The public challenge came from the port industry and the need to have predictive models for a better management of the time required to open or close the port, and also to prevent blank travels. 40% of the travels of the artisanal fishery, for instance, come from travels that they go out, but they don't fish anything, so they come back. The carbon footprint of that is huge, and we need to reduce it, but also false closures or unnecessary closures of ports and extended closures of ports translate into missed opportunities for fishermen. So the challenge is that we usually our observations rely on very heavy and very expensive buoys. Part of the challenges for us is integrated sensors that can actually speak to us in real time, but are cost effective. And using the combination of different kinds of buoys and their integration on predictive models, we are able now to, same thing, have in your phone the real-time conditions, but also the predictions for, let's say, 3 days or 5 days. We have been working on wave dynamics, wind, currents, and other parameters that are of interest for the port. Our predictions are good for a weekly basis right now, but the challenge we are in now, currently, the team of Diego Narváez and Mari Carmen Guerra is working for a much extended period of testing. And this brings me back to plankton. All these, are applications that has to do with oceanographic conditions, so the physics of the ocean, but also the chemistry of it. But all is applied, of course, to the biology. In a world that is relying on prediction for meteorological phenomena, such as these atmospheric rivers, all these little lights, there are huge amounts of rain that travel across atmospheric currents, and actually it means that it's going to rain for a very short time, but with huge, huge intensity. They are called atmospheric rivers. There are extreme events that are getting more frequent right now, and the interaction between this and the coastal ocean, where most of people live, is evident. It's so evidence that is right now in all the international reports on climate change being one of the main targets for concern. So what do we do with this? We plant the coast with sensors that are able to speak to us on a regular basis. That means we are constantly assimilating a lot of data. And for modelers and mathematicians such as yourself, that this may be like business as usual, but in oceanography, really, this is the step where we jump from looking at the one tree to looking at the whole forest for pretty much the first time, and getting it into public databases that allow us to regionalize global models or even localize regional models such as CROCO or others that can actually allow us to adapt the tools that everybody is using to actually the reality of the region we are working on. So that leads me to the only challenge that we have been aware of right now that mixes the two, the physical, chemical, and the biological conditions in a large scale. And that was Mission Microbiome, which I had the privilege to co-coordinate with Alejandro Mas of the Center of Mathematical Modeling for the consortium that we formed, in which Inria was also one of the main participants. And the expedition was really a pluridisciplinary effort to map the entire coast of Chile, but also South America, the Atlantic Ocean, and Africa in an effort to join data collection for genomics, transcriptomic, as well as environmental variables, and gather it together and try to explain how planktonic communities are actually adapting. We gathered the data in order to explain the ecology of the environment and ultimately do provisions for the evolution of the whole. This is the track. So in a 2 years' time, we covered the whole of South America and the Atlantic. We had the first step of the expedition here in South America. The most of the discrete parameters were biogeochemical, physical, but also on diversity. The sequences are already available. We have almost every component of the trophic change already labeled and identified. We just need to put it together with the environmental variables, fit the models, and get an understanding of biomes in a numerical way, more than the ecological approach that we are used to right now. And this is just for fun. It's our buoy in Columo Bay, right next to Concepcion, which is looking at the ocean on a daily basis and getting the information in real time to everybody's phones. This is ColumoMed that you can actually download. And we are looking forward to have these kind of platforms all over Chile, including Tortel, which is sitting in the middle of southern Patagonia and is one of our main projects. So this is just a little bit of the activity that COPAR is engaging into right now. And for us, really, more than being a center that generates mathematical model on a daily basis, we are trying to get to the forest from the one tree we were looking for 10 years ago. So thank you so much, and we are open to collaborations and questions.
Thank you very much. Before giving the microphone to you, we have a question from people watching online. So Luis says, thank for the talk. My question is, how is the transfer of the multidisciplinary scientific progress in oceanography being managed to guide decision makers in our country regarding climate change?
Yes, thank you. That's a very good question. The thing is that for managing decisions, you need different kinds of information. We are used to working with policymakers on quota management for fisheries, for instance, or describing certain areas that we are used to observing. The challenge now is to convince the government, for instance, that we need actually an integrated system of observation. The idea for us is not only being able to look at the ocean, but listen to it as well. And we have discovered that in terms of climate change, the key word for any government is adaptation. And one of the main objectives of the center is accompany society in that road of adaptation by making available data that translate into solutions. For instance, how to are we going to manage ports in 10 years from now, 20 years from now? How are we going to get to the challenge of carbon neutrality in terms of how we use the coastal borderline of Chile? That's a huge challenge, and if we take it part by part, we can actually provide data necessary for decision maker. But it comes to regional counseling, regional governments. It comes also to a higher level of coordination, and the more international the question is, the more we are able to get it to the national reality.
Thank you very much. Any other question from the audience?
You said that you used machine learning to classify different species of microorganisms. Can you tell us about? Can you tell us a bit more about that? What models do you use? Is it supervised? I guess it's supervised. How do you build your training sample, for instance?
Yes, well, it fits from libraries that are available internationally. We connect those libraries of model organisms from laboratories and in situ samples, and we provide the algorithm with certain characteristics that need to be met for this particular cell to be. We don't go to the species because it's really super difficult, but we can go to gender and families, that are known to have certain common characteristics, like diatoms or dinoflagellates. But the ones that interest us the most are very well characterized, in culture, and we can actually feed from different sites, including fluorescence, if the cell fluoresce or have a certain types of fluorescence or not, which probability it has associated to the identity. But also we combine, in the case of the Red Tide program, with the detection of toxins, different types of toxins in the water, at the moment.
Yeah, but what models do you use? Do you use neural networks, for instance, or?
For the detection of cells,
Yeah, for the classification detection. Yeah.
But it is a simple neural model, but we are working for being able to have a more direct output for our make it learn to skip certain kinds of cells and concentrate on size or different characteristics. It has been tried too in microplastic research, because one of the ideas is also to use this kind of technology for actually look for fragments that are different from plankton, which is also something that predators in the natural environment cannot do. They usually just put it in the same category. So using fractals and other characteristics, we might be able to differentiate between a microplastic and a diatom. But it's not really every day very easy to do.
Okay, thank you.
Any other last question? Okay.
Hello. I would like to know more about your monitoring solution. It was developed in-house, or do you make any collaboration with some organization, for example?
Well, we are excellent collaborators because we need to. We can do everything ourselves. Some of the observation system that I showed is obviously brought from abroad, and but the key thing is that integration of sensors is something that we are learning to do here, and in-house. Also the way you go towards constructing our own sensors and integrated them, adapted to the reality of the environment. For instance, in a place like Concepcion, where you combine low oxygen waters with high productivity and such, you need to be able to have a good methane sensor, a good CO2 sensor that will work adequately and in a cost-effective rate. It's tremendously expensive. So we work with the School of Engineering here and with other Center of Excellence in order to get to the point where we can multiply our eyes and ears in the ocean without the money going off in rivers. But we are, I would say that the last 10 years and maybe 5 years have been critical for us to build the capacity for sensor integration here in Concepcion. The more we go, the more we are seeing the point where we will be able to construct our own buoys here for maybe a fraction of the cost.
Okay. What is the main barrier in developing this monitoring system for environmental monitoring?
Well, I would say data quality. I don't know if you know, but for instance, the salmon industry now is forced to have sensors within the cages or in the vicinity of all the cages. The density of the cages is such that it will require like a multiplicity of sensors in each fjord and each channel of the Patagonian system. So it is very expensive. There are solutions and sensors being made and being available, but the quality of the data they provide is really not that good. Mainly because they function for a while and then they need to be calibrated and such, but the absence of calibration means that you cannot use that data after a while. So in order to have good data, you need good sensors, and that is very expensive, and it's out of the question for the industry most of the time. So we are working towards alliance with different companies that produce these sensors in order to make it more available. I would say that right now, if you can imagine what would mean to us in terms of data collection to have all the cages of salmons monitored in real time, that would be super great. But the absence of a cost-effective method for data gathering and the quality of the data, I would say that is a main barrier for us right now.
Thank you very much.
Okay, and I have to present now the last speaker of this morning. It's Veronica Anaya, which is an associated professor of the Department of Mathematics at Universidad del Biobío. She's a doctor in applied mathematics, and she will talk to us about finite element methods for Navier-Stokes equations written in terms of vorticity. Thank you, Veronica.
Good afternoon, everybody. First of all, I would like to thank to the organizers to give me the opportunity to present this work. And to thanks to Professor Mauricio, who is he invited me to present in this activity. In this opportunity, I will talk about a work that we have in collaboration with a PhD student, Rubén Caraballo, and two collaborators from Monash University in Australia and Universidad de La Serena. As you can say, in this opportunity, I will present some numerical method to approximate the solution of Navier-Stokes equation in terms of vorticity. First of all, the outline of my presentation, I will speak something about the Navier-Stokes equation, the variational formulation, the discrete problem, so the numerical method that we proposed, some academic numerical examples, and some the references, the most important references. So, as the title said, we are going to work with Navier-Stokes equations, but in terms of vorticity, the variable vorticity, because there are many works that the authors present the fluid equations in terms of velocity and pressure. But this time, we can add this important variable. We can add this, the vorticity of the fluid. So to begin, I will present, or you can see in the slide, the Stokes equation in terms of velocity and pressure. This term is about the incompressibility of the fluid. We have the boundary condition, and we have to assume that the pressure satisfies this condition to ensure that the pressure is unique. So the idea is to incorporate this variable, the vorticity, in the model. So what is the idea? With this equality, we can add the vorticity to the original equations that they were only in velocity and pressure of the fluid. Using this identity, you can observe that we will have the equations in terms of the three variables. The new variable that we add is the vorticity. And you can observe in this second equation is the vorticity that is the care of the velocity. So the idea is to do the same, but in the Navier-Stokes equation, that there are nonlinear. And another thing that we add in our work is that we assume that the viscosity of the fluid, nu, is non-constant. So if we assume that the viscosity is not constant, we don't have this identity. So in this case, we have to use the following, because as I said, the viscosity will be non-constant. So we will have some term, especially this, that this has the gradient of the viscosity. So, using this identity, considering the vorticity, the non-constant viscosity, we are going to work with this equation. As I said, the Navier-Stokes equation. So our variables are velocity, vorticity, and pressure of the fluid. The usual Navier-Stokes equation in terms of vorticity, taking into account that the viscosity is not constant. The second equation is that that I presented in the first slide is to incorporate the vorticity, the incompressibility of the fluid, boundary conditions. We assume that the velocity is 0 on the boundary. And the last equation is to ensure the uniqueness of the pressure. So as we assume that the viscosity is not constant, we have to assume to prove the existence and uniqueness of the weak solution, and our method that we propose is well-posed, we have to assume this on the viscosity. See, this parameter, R star, will depend on R, that R is, it will take some values if we have in 2 or 3D. I have to say that this work is presented. We propose the numerical method, and we obtain the existence and the well-posedness of the method in 2 and 3D case. In addition, we assume that the viscosity is bounded. See, we have to assume these things to have the well-posedness of our method. The coefficient sigma, we assume too that this is bounded, and the data, it belongs to this space. So this is the equations that we are going to work. Only to some notations. Some notations, we assume that, or we do note, we do note that X is these product spaces. So if we have B, theta, and Q belongs to these product spaces, and we will have this norm. See? We will define these norms on the respective phases. So we have to remember too this green formula, because I present before the continuous formula equations of the Navier-Stokes equation, but we have to present the weak formulation, and then we have to prove that this well-posed. It means that it has a unique solution, and then we can propose a numerical method that it will base in finite elements, and we have to prove that the method is too well-posed. So the variational formulation, we have to find velocity, vorticity, and pressure in the spaces that I gave it before. This is obtained, this variational formulation is obtained from the equations that I present before. We have to multiply by the test function, and then using integration by parts, using the boundary condition, the assumptions that we have, we arrive to this formulation that is called variational formulation. You can see the bilinear forms A, B. They have this form, the functional, the right-hand side, and I put in blue because these two terms, they are the addition where we assume that the viscosity is nonlinear. And I have to say that if we assume that the viscosity is constant, our method is well-posed too. And in addition, as the bilinear form before, it was not possible to prove that that is well-posed, because we couldn't prove some bonds over this bilinear form A. So the technique is to add some terms, these terms that I put in red. The idea is to add these terms that they came from the continuous equations. If you remember, the first equation that is introduced that is with the vorticity. Yes, I said that the vorticity is the curve of the velocity. So the idea is to introduce these red terms that is like I am introducing zero terms. Yes, so I need to introduce this because they help us to prove the well-posedness of our problem. So the method that I will present is a finite element method. It's called mixed finite element methods because of the form that we will have then, and is augmented mixed finite element method because we add these terms. The bilinear form B is the same that I presented before, and the functional F is the same. Only we add these three terms in red. This is a previous work that we have with Ossin equation. It's a linear equation. It's an equation in fluid mechanics too. And we assume two variable viscosity. So the idea is to linearize the Navier-Stokes equation and then use the techniques that we have in this work. To prove the well-posedness of our variational formulation, we will use the fixed point theory. Fixed point theory, the idea is to linearize in the terms of the nonlinear term of the Navier-Stokes equation, and then use the Babushka-Bresci theory to prove the well-posedness of our method. So for this, we need to prove this lemma. This is an in-sub condition. We can prove this. In addition, to have all the hypotheses of the theorems that I mentioned before to prove the well-posedness, we have to prove this bond for the terms of the bilinear forms. So we can prove this using a typical Cauchy-Schwarz, Young, and Poincaré inequality. So this lemma is previous to prove the well-posedness of our nonlinear problem. Here you can observe kappa 1 and kappa 2. They are related with the red terms that we add, the augmented terms. They have to satisfy some bonds. And in addition, our data, the viscosity, the gradient of viscosity, the divergence of beta, this is the approximation of the velocity, has to satisfy this inequality. So with this, we can prove that the bilinear and antilinear form are bonded. And as I said before, we are going to use a fixed point theory to prove that our nonlinear problem is well posed. Is in this. I'm sorry, no, before I say something about the bilinear form A, that it was this bilinear form with the blue terms and the red terms. Now I separate the part that is linear and nonlinear. So the idea is, as I said, to use a fixed point theory. So we linearize the nonlinear term, assuming that we have some approximation of the velocity. So we have a linear problem that we can prove that is well posed using the Babushka-Bresci theory. So thanks to the continuity that we proved before, the bonds that I present in the last slide, we can have the solvability of the linearized problem. See? So we can assure that we have a unique U velocity, vorticity, pressure in these spaces such that they satisfy the linearized problem. So this is the linearization of the nonlinear term of the Navier-Stokes equation. In addition, we can prove that the solutions are bounded in terms of the data. So all only some results more to prove that the nonlinear problem is well posed. So we have to have some fixed point operator. We have the same assumptions over the parameters kappa 1, kappa 2, and the data, the gradient of nu. And we have some set over, we are going to define the operator J. So the idea is to prove that this operator has a unique fixed point. Finally, we can prove that the two problems are equivalent. I mean that if we have all the assumptions about the parameters, kappa 1, kappa 2, about the gradient of the nu, the operator J has a unique point, and this is equivalent to we have a unique solution our previous problem when we have the three variables: velocity, vorticity, pressure, in these spaces that I presented in the beginning. So that was about the continuous problem. Now the method that we are going to present is based on finite elements. So first, some notation. There will be the partition of our domain. H will be the maximum of the diameter of any. I'm sorry, I didn't say. Our domain will be in 2 and 3D. So our shape partition, say regular partition, will be triangulars or tetrahedron. So there will be the diameter of each triangular tetrahedron. In this opportunity, we are going to consider finite dimensional subspaces that are subspaces that are continuous spaces. So the method is conforming, talking about the space. We are going to take some finite dimensional spaces for velocity and pressure, spaces that satisfy this in-sub condition that is for Stokes' problem. So our Galerkin scheme, you can observe that it has the same form that I presented in the continuous problem, because it was defined for the product space that I presented before, and I said that these XH, WH, and QH are the subspaces of the continuous spaces, so they will satisfy the same variational formulation that I present for the continuous problem. Yes, as I say, A, B, and F will be the same that I present in the beginning, the variational formulation. For this numerical scheme, we can prove the following, considering the same assumptions of the continuous case. See, we have to assume that the parameters satisfy all the bonds that we need. We have to assume the small data. Do you remember this is the F? It begins, it comes of the equation, is the data. So we have to assume that it is small. And we can prove that there exists a constant independent of the parameter of the mesh, that we can prove that this bond. We can prove this bond for the three variables. You can observe here that this is the continuous, is the solution of the continuous problem, and this is the velocity of the discrete formulation. It says that this UH, omega H, and PH are the solution of our discrete problem, our finite element method. I said that we are going to take a pair that is stable for Stokes' equation. I present here's one example, taking Taylor-Hood finite element for velocity and pressure, and for vorticity, we can take continuous or discontinuous polynomials. Yeah, there is no restriction about the the space for the vorticity. So this is this space, the Taylor-Hood pair. This is the space to approximate the velocity, the pressure, and as I said, we are going to approximate the vorticity with continuous and discontinuous polynomials. They are going to, the approximations will be polynomials, see? Polynomials over the triangulars or tetrahedron. These were the spaces, but we have to prove that they approximate in well-formed or continuous solution. So we assume that we have a continuous solution, a unique continuous, a unique discrete, and the idea is to using the approximation properties of the spaces that I presented, that we can prove this estimate. There exists C depending of the parameter of the mesh, and we can prove this estimate. Another example is taking another pair of mini elements. This is another pair for stable for Stokes, and again for vorticity, continuous or discontinuous. These are now the spaces for pressure, velocity, and vorticity. Again, for these selected spaces, we have to prove that they have the correct approximations for our continuous solution. Only academic examples. We are going to take this square, SER1 square. We have a manufactured solution, velocity, pressure, vorticity. And in this opportunity, we take this as a viscosity, variable viscosity. We have to take these parameters to satisfy all our results. And I present this table that you can see here. H is the parameter related with the mesh. The idea is to reduce this parameter, and we have to prove that this error, the approximation between the continuous or the difference between the continuous and discrete, it has to tend to 0. It has to decrease. For the 3 variables, you can observe velocity, vorticity, pressure. It decreases. And this is the order of convergence. The order of convergence is 2 for the 3 variables. That is where we prove all the theoretical results. The last example, we have now the cube, unitary cube. We have the exact solution, manufactured exact solution. This time we put this viscosity. The parameters again, we have to select the correct parameters to satisfy our theoretical results. And again, we have that the error tends to 0 for the 3 variables, and the order of convergence is 2. That is expected that we obtain in our theoretical results. Some references about this work. So we have these 3 words about the equations of fluids, Brinkman, Oseen, and Navier-Stokes, assuming the variable viscosity and written in terms of vorticity. Thanks for your attention.
Thank you.
So what's the point of using vorticity or reformulating the equations in terms of vorticity?
Okay. Because we see that there is important to obtain the vorticity, and specifically our method approximate the vorticity with the same the approximation is this, how do you say? We don't lose the approximation, I take the vorticity, because, I'm sorry, again, some works, they approximate velocity and pressure. And then you, using post-processing, you can obtain the vorticity because this is the curve of the velocity. But we don't have the correct approximation because we have to derive the curve of the velocities at derivation. So you don't have the good approximation, I say, if you solve the equation using as a principal variable the vorticity. And another thing, a positive thing about our method is that you obtain directly the vorticity. You don't have to do any post-process. And you have the, as I said, you can approximate the vorticity using any discrete space. It could be continuous, discontinuous, the polynomials, the degree of the polynomials. No, there is no connection with velocity vorticity. So this is the advantage of this, or to obtain directly this variable that in some problems, some applied problems, it's important to have the vorticity. Okay.
Can you show the variation of formulas?
Yeah.
Yeah, so.
I'm sorry.
Yeah, so what is the interpretation of A and B? There are two functionals.
Yeah. No, B bilinear forms A,
Bilinear forms.
B, and this is the functional F.
F, okay. So A and B are just bilinear forms that depend on the vorticity, the velocity, and the pressure.
Yeah.
Okay. All right. Okay. Thank you.
You're welcome.
Okay. A last question, Chair? Okay.
Yes, thank you for the talk. I was wondering if there is a difference between the two finite element methods you proposed in the two-dimensional framework. Is there one that is better than the other, or?
No. You can choose any pair stable for Stokes. They were the same. As I present in the, I'm sorry, I present only one for one pair, but they behave in the same way. We have the order of conversion, two order conversions with the degree, the lowest degree. So there is no difference between them. Yeah.
Yes, thank you. Thank you very much to Veronica Anaya and also Camila Fernandez for her remarks and for sharing the first scientific session of the conference. Now we invite you to move outside to where lunch will be served. And please, we are going to call you back in something like an hour. So please be back when we tell you. And we hope that lunch will provide an enriching networking opportunity, fostering virtuous connections and scientific opportunity. Thank you very much.
Thank you.
$150. we're going to be back. 2 p.m. at the most.